Hey guys, today we're going to talk about some nuclear chemistry. It's basics of chemistry and the very fundamentals of how the atoms and molecules are formed and the basics of the periodic table. So I'm just going to get right down to it. First, a little bit of history. I'm going to draw an atom right here. Okay, so let's see. That's the nucleus, the electrons. So a long time ago, when Niels Bohr introduced the atomic model, we all kind of thought that the atom is kind of like the planet, or there is a central sun, or the nucleus heavy with the protons and neutrons. And then we've got these little particles, electrons, orbiting the nucleus like planets. Now we went along with that model for quite some time until we realized that that's not how that works. But the atom right here, I don't know if you're familiar with this, it's the silicon atom with the electron configuration of 2, 8, and 4. So these shells, they're called orbitals. We don't call them orbits. And they're all numbered 1, 2, 3. The skull, the principal, quantum number. So these are the orbitals, the shells of the atom, also referred to as the principal quantum number, shell 1, shell 2, shell 3. So if you look at the silicon atom, it's quite beautiful. It's got 2 electrons in the first orbital, or the first quantum. We also call them as K, L, M, N, and so forth. So that's kind of how we started off with when it comes to the atoms. We were pretty basic. We thought of them as little planets orbiting around the nucleus, that's the sun, and then later realized that's not how that worked. But it still sort of applies to a certain degree, and I'll tell you why it still applies, why the particle and the wave nature still coexist. But before we go down to it, let me briefly explain the atomic model. These shells, the first shell has 2 electrons, the second shell has 8. The third shell of silicon has 4. So after some time, we thought that these things are orbits. So then we discovered that, hey, these orbits, they actually have suborbits, and they're not exactly one orbit at a time. So these one little things, they are split up into further suborbitals like this. They're called the S. This is the P. And here it'll be like mini orbitals that sort of circle the whole thing. So they're like concentric rings in this particular model. So it'll be like S, P, D. Then it goes to F and so forth. So these SPDs, Fs, they're called the angular quantum numbers, angular quanta, azimuthal quantum. Well, there's multiple different names of these, but all these really are is the angular momentum of the electrons on different planes. So then that becomes the angular quanta. So the SPD, they're all part of these shells. So this is the first shell that is a very small shell, can only hold 2 electrons at a time. So it only has the S shell. Now the S shell can hold 2 electrons. The P shell can hold 6 electrons. So 2, P shell, 6 electrons. D can hold 10 electrons. So together it sort of adds like 2, then 2 plus 6, 8. Then the final one, 6 plus 2 plus 10, 18. So the 18 in the third shell is the maximum amount that an atom can hold in the third shell, which is the M shell. So how does this work? And what are the electrons doing when we look at this whole picture? So for a long time, we went along with this whole theory that the electrons are just sort of spinning around the nucleus like planets. And then came quantum physics and said all of this is basically just horseradish. So I said, we are thinking two-dimensional. We're thinking too far two-dimensional, and it started to feel like we're back at the Earth is flat conundrum. We're three-dimensional beings, but we tend to think very two-dimensional sometimes, and sometimes that lands us into a big trouble. So for a long time, we thought this two-dimensional plane of orbiting electrons around, and then that's not what's happening. Quantum physics came in and said electrons, the atoms, are actually more like, it's less like the planet and more like a water-filled balloon or a tennis ball, where you have a bubble sort of thing. It's filled with charge, positive and negative, and it sort of is like a big giant, well, not a big giant, a small tennis ball, microscopic, very small. It's like a bubble, it's like a water-filled balloon. And inside, the electron is actually an electron cloud as opposed to these little particles. So now what? How is a tennis ball or a water-filled balloon translating into the circular model that we are all familiar with? So there's a little thing that started when Schrodinger was discovering his equation for three-dimensional or spherical harmonic motion or cubic harmonic motion. Before that, we sort of thought a harmonic motion like a pendulum moving back and forth. And we were familiar with the simple harmonic motion equation, which basically was how we understood any kind of circular or harmonic motion. But when you think about a spring or a pendulum, they are very linear. Apply the same geometry to three-dimensional plane, and if you ever come across a video of a water-filled balloon bouncing on a surface or a tennis ball bouncing on a surface, you'll see that it takes multiple different shapes as it bounces, and it's quite intriguing to understand how a tennis ball, as it bounces, it takes these different forms as it's bouncing. It's almost like it's stretching in different planes and sort of like boing, boing, boing. Its shape is changing, and the fluid inside, let's say a water-filled balloon, is stretching and contracting and expanding in harmonic rhythm and harmonic fashion. So that's called three-dimensional or spherical harmonics. So electrons behave exactly the same way inside the atom. So the atom is your water-filled balloon that is vibrating, and the fluid is sort of just jiggling around in these formations. Now, for those who are sort of familiar with waves, like you've got a guitar string, okay? So a guitar string vibrates, or a piano string vibrates in many different forms. It will vibrate in infinite forms at the same time that are called harmonics. It's just really, really fast, like it's just really fast. So you'll see that a string vibrates in many, many different ways. It's called harmonics. So this is two-dimensional harmonics, okay? For a water-filled balloon stretching and contracting under nuclear forces, and whatever force an atom is subjected to, we actually still don't know what kind of forces are involved besides the nuclear and electrostatic and magnetic forces that are acting inside the atom. So the moment we started thinking of atoms as water-filled balloons, just sort of sponging around. The picture started to emerge quite clearly that if you look top down, it will look like water ripples. So we're actually looking at it from a two-dimensional perspective, and it sort of looks like ripples, right? If you throw a stone into the water, it'll form ripples. Now those ripples, if you were underwater, you will have a better picture of what these ripples are going to look like. So if you look at a bouncing ball, that's kind of like a jiggly kind of gooey ball, like a water-filled balloon bouncing up and down. Look at it from the top view, it's going to look like ripples. And I might put a clip in this video or share the video of a ultra slow-mo bouncing balloon. So that's how we thought the atoms work, kind of like ripples. So we're looking at ripples of this charged matter inside the atom, which we think is electrons, but it actually could be further more elementary than that. And it's just coagulated cloud sort of rippling around that we think as electrons spinning. So coming down to the spdf orbitals, suborbitals that I mentioned as the angular quanta. So we used to be familiar with K, L, M, N shells, and each of these shells were divided into subshells, SP, SPD, SPDF, and so forth, where S holds 2 electrons, P holds 6, 2, 6, D holds 10, so 2, 6, 10, and F holds 14. So these are actually these harmonics of the spherical tennis ball, spherical balloon, and each of these shapes, I'll tell you exactly why the P shell has 6 electrons and D has 10 electrons, and it's really quite intriguing. So when Schrodinger's equation is the equation that gives us the solution of the three-dimensional spherical harmonics, Schrodinger wave gives us solutions that describe that in the S shell, it's spherical. Almost think of it like a drum membrane going up and down like this. So that's the first orbital, which is the S orbital. Okay. So now, after further solving the Schrodinger wave equation to the second harmonic, which is the P. So the P harmonic will have 3 different configurations, okay? So you'll have something like this. Okay. Let's break this down into axes. Okay, so the z-axis, x-axis, y-axis. So the second harmonic level of the atom is sort of like this. Now if you stretch this into all 3 dimensions, you will have something like this, or that would be on the, or something like this, translating them into all 3 axes. So then, at the P shell, the configuration of the spherical harmonics can coexist in 3 forms. So each of these is an electron spin. So this would be a positive spin. This will be a negative spin. So by spin, I mean they're in 2 different signs, like negative or positive. So going by the same plane, this is positive. So this is the configuration of the P orbital. The P orbital, which sometimes, if you have taken any kind of chemistry, you will probably remember this. Something like that, right? So 6. This can hold 6 electrons, one going upwards, one going downwards, one going left, one going right, one going orthogonally left, one going orthogonally right. So six electrons. So these are the three configurations that a p orbital can be in. So it can hold 6 electrons. Now going down further to the d orbital. The d orbital we know from Schrodinger's wave equation that it can hold 10 electrons. So how does that work? So if you look at the slow motion of the bouncing balloon footage, you will see that the configurations sort of look like this. Okay, so these are like bubbled up along the z-axis, like this. So it's like stretching and contracting, and then either the electron is going to be in this little ring or this dumbbell. So this is the cloud. This is the cloud of charge that we thought is the electron looking from the top down, when it's actually a shape of a three-dimensional sphere just vibrating with a fluid inside, with a medium. It's some sort of a Gaussian medium inside. So that's one configuration that it can also simultaneously exist in a few other configurations. Could be sort of like this. Translated into three different axes. So this basically z, got this x. So if you translate this into 3 different axes, you will have this times 3. Okay. So then you've got this, then 3 times of this configuration translated on 3 different axes. Then you've got an orthogonal axis, which is basically y, x. So you'll have a bubble along the y-axis. And you'll have a bubble along x-axis. Okay, you have to look at this in slow-mo. So these shapes, they're going to be different types of shapes of the balloon forming. So then we look at, this is our d orbital. D orbital is the state of the balloon in which these harmonics are simultaneously happening. So the balloon is vibrating in all these kind of different shapes. So sometimes we call it the d square shape. This is like a d, x square, y square. They're just names. Don't think of in terms of algebra. This is quantum algebra. So think of this as more like how many different shapes is the balloon, the water-filled balloon vibrating in? Except the water is a Gaussian charge, known as the electron cloud. And it's bound by the nuclear and electrostatic forces, which makes the boundary of the bubble. So the bubble is sort of gyrating in 5 different ways. We got 1, this is 1, and then 3 simultaneously. So in this harmonic, which is called the third harmonic of the Schrodinger's wave equation, we have 5 different forms. So 3 plus 1 plus 1, 5 different forms. So each of them can hold an up or a down spin. So you've got, this is 1 electron bubbled up in red, and this is another electron in a separate phase, just kind of like a ring forming around here. So we'll call that configuration 1 with up and down spin. Same thing here. So we apply it. Every configuration is going to have an up or a down spin. So that's what's going to give us the maximum number of electrons. And this d orbital is 10, 5 times 2, 10 electrons. So you can see it's kind of eye-opening as to how we thought that these were little planets revolving around the nucleus, and then ended up realizing that this is actually a gyrating ball. It's a gyrating ball exhibiting spherical harmonics that have different shapes. Like string has different shapes when it's undulating along one axis. Now think of a ball as a string in all 3 dimensions. So this is how it's going to be oscillating. So that defines the electron orbitals when we look at all these vibrations and look at it from 1 dimension or 2 dimension. That's when we start seeing that, hey, this is starting to look a lot more like the same as the classical model of where we define the electrons were sort of around the nucleus. So that's what gives this picture from top, viewing these harmonics. And they're not really moving in circular motion at all. They're actually just shifting phase magnetically from top to bottom, bottom side to side, or up or down. So that's basically how it is. So let's come back to one of the atoms that we were discussing. We're looking at silicon, right? Silicon is 2, 8, and 4. So go back to the old model, first principal quantum number 3. Okay. So now let's see what's happening in the shell 2. Okay. Shell 2 has 8 electrons, which is 2 in the s orbital, which is the mini orbital. That means it's gyrating in a shape of a ball, concentric ball. Then you've got the p orbital, okay? It's got 6 electrons in the p orbital, and it's completely full. So that shell number 2 is stable. Now we'll look at the shell number 3. Okay, shell number 3 has 1, 2, 3, 4 electrons, okay? So 4 electrons, there's an order to how these shells fill based on the energy. The S shell, the subshell S, will fill first with 2. And then you've got the P shell will fill with 2 electrons. So it's going to start to look like the first one is full. So it's going to be up, down, spin. That's the 2. Okay. Then you look at the second one. It's got up, down, and it's completely full. Now the fourth, this shell right here, 3, we've got the s orbital is stable, but we've got the electrons. There's only 2 electrons. So the way we fill these orbitals is that they're first going to be half filled with the same polarity. It's not going to be like up or down here. It's first going to fill one direction, then it's going to fill the next direction. So this gives silicon some interesting properties. As you can see in the third shell of silicon, we've got 4 electrons, which makes it a very, very interesting element, because it could either give all of these 4 electrons and be stable, or it can also take electrons. It can take 4 electrons. Let's give it 4 electrons. So it can give and it can take 4 electrons. But something has to actually be compatible with silicon to give it 4 electrons, or it's going to give its 4 electrons. The other possibilities that it can have to reach a stable point is that it can actually also give just these 2. So then this becomes empty. still a valid, stable configuration. So it doesn't have to actually give this. It just needs something that will take 2 electrons, and it will gladly give those 2 electrons to that element. Or if it can find something that wants all electrons, it'll just give all 4 electrons to make the other element stable. And that's the basis of chemical bonding. And silicon is the elder brother of carbon. Carbon is same properties or in the same family as silicon. It just doesn't have that. So if we were to look at carbon, carbon has a similar structure. It's got 2 in the s orbital and 2 in the p orbital. So that brings us to the next part, the periodic table. The periodic table is extremely important. That's the basis of all chemistry is going to become clear if you know how to read and understand the periodic table. And I'm going to go as far as telling everybody to memorize the periodic table and learn how to read it. So whether you memorize it or not, I'll tell you an interesting story. This was a long time ago. I was meeting a client in a coffee shop called Zeitgeist in Seattle, near the Amazon complex. He worked at Amazon, had a project for us. So we went to the coffee shop, and the coffee shop actually had a periodic table theme to it. So I went to the counter, and the lady said, "Hey, can you write the periodic table and your coffee's free? And I'll comp you whoever's drinking coffee." And I said, "Of course I can." And I wrote down the entire periodic table on a napkin, and my coffee was free. So whether you're doing it for a free coffee, a party trick, I still recommend you learn the periodic table. So if you are one of those who'd like to memorize, there's many benefits, which I'll show you exactly what kind of benefits you can reap, and you'll quickly understand properties of elements based on their families. So if you want to memorize the periodic table, start with this line. Okay. We call it the baseline. Starts with potassium. Okay, so calcium. Potassium, calcium, scandinavium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, bromine, and krypton. So if you start with this, then you can work downwards. Should be about 18 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 17, 18. Then you work up down. So sodium, lithium, hydrogen, francium. So these are going down, these elements are going to have exactly the same properties, or very close, when you go up and down during columns. And they will have the same amount of electrons in their outermost shell. Their configurations will be very similar, and hence the similar properties. So these are your alkaline earth metals. So these are your alkaline metal area. Lithium, sodium, potassium, rubidium, cesium, francium. These are your alkaline earth metals. Then this middle area starts to kind of become sort of ambivalent as it starts to go towards metallic, more diverse portfolio. These are your inert gases, so it would be helium, helium, neon, argon. So we're going to work this way. Ytterbium, lanthanum. So right here, these are your lanthanides and actinides. They're actinides, your radioactive series. We put it here separately, and I'll tell you that why when we go to why these elements are organized the way they are. You'll see a very beautiful pattern emerge. So the benefit of memorizing the periodic table this way is you learn the properties of these elements and then track down their families like nickel, palladium, platinum, copper, silver, gold. You start to see a beautiful pattern. Zinc, cadmium, mercury. I forgot if it's xenon or radon, something like that here. I could be wrong. I'll probably just make it like xenon here, radon here. So chlorine, bromine, iodine, adenine, chlorine, phosphorus, silicon, aluminum. So silicon is in the same family as carbon. Carbon, silicon, germanium, tin, lead, similar families. Okay, so fluorine, oxygen, nitrogen, carbon. So this is the very basic form of the periodic table, and these are organized in terms of the atomic number. Your hydrogen is going to be 1, helium is going to be 2, and lithium is going to be 3, 4, boron, 5, 6, 7, 8, and so forth. You go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, goes all the way that way. So you're going to start seeing a pattern emerge here. 1, 3, okay? It's going to be 8. So 3 plus 8, 11. Okay, so it's going to be 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, and so forth, going all the way that way. Now, you'll see that this has a difference of plus 2. 2 has a difference of 8 plus 8 plus 8. I bet you the difference for this one will be 18. And it's going to be 32. So 19 plus 18. That's going to be 37. So that way you will see that these numbers 2, 8, 8, 18, they're starting to look a lot like the KLM shells. 2, 8, 8, 18. So that's one thing you're going to learn. Is immediately you'll be able to pinpoint the atomic number of any element, and then from that derive the electron configuration of that particular element. So let's take iron, for example. It's going to be 19, 20, 21, 22, 23, 24, 25, 26. So 26. So we're going to go down and take a look at iron. as how the iron atom should look at the electron, at the atomic number of electron. So learning the periodic table doesn't only give you a quick reference of what their atomic number is, it gives you an idea for their electron configuration inside the atoms as well. Like, let's take a look at sodium. Sodium's got 11 atomic number, and it's going to be like this. So 2, 8, and the last shell is going to have 1. So that tells you right there 2, 8 is filled, and then 1. So sort of a pattern emerges that we already discussed. And all of these alkaline earth metals are also going to exhibit a similar pattern. So magnesium is 12. So I guarantee you magnesium is going to have an electron configuration of 2, 8, 2. It's going to be 2 right here. The S shell is going to be filled, and then it's going to have something like this. It's going to have the S orbital filled and the 6p orbitals filled, 8, and the final shell, the third shell, is going to have 2 s orbitals filled. So that is going to be our magnesium. So just by looking at the periodic table, we can quickly derive what type of behavior each element is going to have. Like the silicon is going to behave like carbon, germanium is going to behave like silicon, and tin is going to behave like germanium, lead's going to behave like tin. So when you go deeper into inorganic chemistry, knowing the periodic table comes with great benefits. So let's drill down to how these orbitals for an iron should be filled. And iron is a very important element that inorganic chemistry people are excited about. So we know from the periodic table it's got an atomic number of 26. So now going by our octet rule, which is basically 2, 8. Now 10 will be filled. Now the rest is 16. 16 electrons are yet to be accounted for. Now it should either be 8 or it should be 18. So that's where the rule kind of sort of falls apart, and then we go drill down into the subshells. So the subshells, it's important to know that the S shell is going to fill before the P shell. So the way this is going to behave is like this. Let's write down our principal quantum number, final quantum number. Each of these shells, these are shell 1, shell 2, shell 3, shell 4. Let's say it's got S. We call it S1. Okay. So the second shell usually has 8 electrons, so it's going to have an S orbital and a P orbital. That gives us our 8. The third one is going to have an s orbital, a p orbital, and a d orbital. Okay, so instead of telling how many electrons are in it, we're just going to call them something like 1s, 2s, 2p, 3s. The number 2 corresponds to this 2. 1, 3, 4, 5. So just so we can remember what we're doing here. So 4s, 4p, 4d, 4f, and so forth. Okay, 5s, 5p, 5d, and this distribution sort of starts to follow a Poisson distribution. It goes big towards the center, sort of like this, and then starts to settle down. It doesn't keep going crazy like 32, 64, and then you have an element with 128 in the center. No, that doesn't work that way. Maybe on some Jupiter or something, but here it will start to calm down, 6s, 6p, sort of like that. So when we start to account for the 16 remaining electrons as to how they're going to go. So we already know that these two are accounted for. 2 and 8, they're fully full. They're full. So now, coming back to the structure of iron, and we're going to try to fill these orbitals because we know the s orbital has 2 electrons, p has 6, d has 10, f has 14. So the atomic number of iron is 26. So it has enough to fill the first 2 principal quantum numbers, the first 2 orbitals, the shells, or the K, L, or whatever you call it, 2 and 8. So 10 are accounted for. We're left with 16. So when we go to fill these orbitals, we start, this is filled already. So that's filled. This is filled. This is filled. So first and second layer, there's the first, that's the second, they're filled. So we're going to start filling the third layer of the atom. So it's going to be something like, it's going to be iron. So the first is full, the second is full. Trying to figure out the third. So when we fill these, we go in an order like this. We fill this, we fill the second S, then we fill the second P, then the 3S, then we fill the 3P and the 4S, then we fill the 3D, 4P, 5S, sort of diagonally, right? Harry Potter a little bit? No? Well, however you see it, it's kind of like a snake going through like this. So we're going to fill the 3s first. So 3s, so whatever's remaining is 3s2. We gave it 2 electrons. Then we're going to fill the 3p. So 3p6. So after 3p, diagonally, we're going to fill 4s. 4s2. So this is now starting to go in the fourth shell. Now, it's interesting to see that the energy of the orbital 3D is actually more than the energy of the orbital 4s, which is why it fills after that. So it's sort of the think Schrodinger for this, all this beautiful stuff. So after 4s, how many is this? 10? 10 is accounted for, and then we've got the 3D. The remaining 6 is going to go to this. So you see, we filled these two. So 1s2, 2s2, 2p6. So that's your iron configuration right here. So if we were to combine everything that's in the third layer is how many? We've got 6 plus 6, 12 plus 2, 14. And then we're left with 2 electrons in the fourth shell. So 14, that's going to be interesting. In the third layer, you've got 2, so we've got 2s. Then we've got the p completely full, so it's going to be, these are the p electrons. Okay. Then you've got 3ds. So 3ds, something's going to be like this. 6 there, missing 2. And then the fourth layer of the atom, something like this. So this is the electron configuration of iron. So most commonly, the outermost shell, the fourth shell, has 2 electrons. So it's got a valency of 2 valence electrons. And it has the potential to give those 2 electrons. So if we were to just look at the third shell and the fourth shell of iron, it's going to be, this is the third, 3s2, then you've got 3p6, and we also have the 3ds. 5 configurations, right? We got our tennis ball bouncing scenario, the balloon bouncing scenario we discussed. So it's got 6 in the layer. So it's interesting how this thing is going to be filled. And then the fourth layer is going to be 4s2. So what happens? It's an interesting scenario here. We've got an unstable layer in the third shell where it has potential to give one of this polarity right here and two of this here. So the straightforward valency of 2 comes from here. But then iron also has a third valency, which is the valency a second valency of 3. It can potentially give one more electron. And it's probably going to be the one in the 3D layer, the lone electron that's going the other way. That's the next electron. So it has potential to give one more electron, which is what gives the iron the dual valency possible configuration. So interesting, isn't it? How many things you can derive from the periodic table and some basic knowledge of how the atom is organized. And the way these reactions happen is how many electrons does an element have to give or take? So potentially it can give these two, or theoretically, it can take 1, 2, 3, 4 electrons. It can actually take 4 electrons and become stable as well. Now, is there an element that could possibly give iron 4 electrons in the 3D layer? We don't know yet. We don't know if any kind of ionized supercharged cannon can create that kind of element that will react with iron. But in the ground state, iron's most likely the lowest energy configuration is going to be, it's going to give these little electrons, and it's possibly going to give one electron right there that gives it the 3 valency and the 2 valency. So when these orbitals are filling, we know that they fill in one direction first, then they go the other direction. So that kind of sums up the entire inorganic and organic chemistry. Now, the next thing is types of bonds. Now, there is covalent bonds and ionic bonds. Covalent bonds is where 2 elements are sharing the same electrons, and the ionic bonds are where one is giving and the other is taking. The 2 ions are interacting. That's something else we can cover another time, but this is the very fundamentals of chemistry.